The dawn of the 20th century found physics at a crossroads. The established principles of classical physics, which had been the bedrock of scientific understanding for centuries, were being challenged by new experimental evidence that didn't quite fit the existing theories. Classical physics, rooted in the predictable laws of Newton and Maxwell, seemed to explain the universe. Newton's laws of motion and Maxwell's equations of electromagnetism had provided a comprehensive framework for understanding the macroscopic world. Yet some phenomena, like the behavior of light and atoms, defied explanation. The wave theory of light couldn't fully explain the photoelectric effect, and the classical model of the atom couldn't account for the stability of atoms or the discrete spectral lines emitted by elements. Enter a young Danish physicist named Niels Bohr. Bohr was deeply influenced by the work of his predecessors and contemporaries, but he was also willing to think outside the box.
In 1913, I proposed a radical new model of the atom. My model was a departure from the classical view and introduced concepts that were revolutionary at the time. My model was built on an audacious idea. Electrons in atoms could only exist in specific energy levels, or orbits. These orbits were quantized, meaning electrons could only occupy certain allowed energy levels. Imagine these orbits as steps on a staircase. An electron can be on one step or another, but not in between. This quantization was a key departure from classical physics, which allowed for a continuous range of energies.
When an electron jumped between these levels, it emitted or absorbed light at a specific frequency, creating the distinct spectral lines observed in heated elements. This explained the previously mysterious spectral lines of elements, like hydrogen. Bohr's model elegantly explained the spectrum of hydrogen, the simplest atom. The model's success in explaining hydrogen's spectral lines was a significant validation of the quantum theory. This was a triumph for the nascent field of quantum theory. It showed that quantum mechanics could provide accurate predictions where classical physics had failed.
Light, it seemed, wasn't just a wave, but also came in discrete packets of energy called photons, as Albert Einstein had proposed in 1905. This dual nature of light was a cornerstone of the emerging quantum theory. But the implications of my model were profound and puzzling. It suggested that the behavior of electrons and other subatomic particles was governed by probabilities, not certainties. It suggested that the subatomic world operated by a different set of rules than the familiar macroscopic world. This was a radical shift in thinking, challenging the deterministic view of classical physics.
This was just the beginning of a revolution in physics. Bohr's model paved the way for the development of quantum mechanics, a theory that would fundamentally change our understanding of the universe and lead to numerous technological advancements. Albert Einstein, already a scientific superstar for his theories of relativity, played a pivotal role in the development of quantum theory.
In 1905, the same year I published my groundbreaking work on special relativity, I proposed a solution to a perplexing problem, the photoelectric effect. This effect, in which light shining on a metal surface could eject electrons, couldn't be explained by classical physics.
Einstein's solution was both elegant and revolutionary. He suggested that light, previously thought of purely as a wave, could also behave as discrete packets of energy called photons. The energy of each photon was directly proportional to its frequency.
This meant that only light above a certain frequency, and therefore energy, could dislodge electrons from the metal, perfectly explaining the photoelectric effect.
Einstein's work on the photoelectric effect earned him the 1921 Nobel Prize in Physics and cemented the concept of light quanta. But ironically, Einstein himself grew increasingly uneasy with the implications of quantum theory.
I famously declared, "God does not play dice with the universe," expressing my discomfort with the probabilistic nature of quantum mechanics that would emerge in the following years.
Despite his reservations, Einstein's work on light quanta laid a crucial cornerstone for the quantum revolution. While Bohr and Einstein grappled with the nature of light and electrons, another giant of physics, Ernest Rutherford, was probing the structure of the atom itself. Their debates and discussions were shaping the future of quantum mechanics, but Rutherford's work was about to revolutionize our understanding of the very building blocks of matter.
In 1911, working at the University of Manchester, I conducted my now famous gold foil experiment. This experiment was designed to probe the internal structure of the atom, which was still a mystery at the time. We were eager to test the prevailing theories and uncover the true nature of atomic particles. In this experiment, alpha particles, which are positively charged particles emitted by radioactive materials, were fired at a thin gold foil. The setup was meticulously designed to observe how these particles interacted with the atoms in the foil, providing insights into the atomic structure.
Rutherford and his team expected most of the alpha particles to pass straight through the foil with slight deflections, based on the prevailing plum pudding model of the atom, which pictured electrons distributed throughout a positively charged sphere. This model, proposed by J.J. Thomson, suggested that the atom was a diffuse cloud of positive charge with negatively charged electrons embedded within it. Instead, they observed something astonishing. The results defied the expectations set by the plum pudding model and hinted at a much more complex internal structure of the atom.
While most alpha particles did pass through with minimal deflection, a small fraction were deflected at very large angles, some even bouncing straight back. This was a surprising and puzzling result that suggested a new model of the atom was needed. This result was completely unexpected and could only be explained if the atom's positive charge and most of its mass were concentrated in a tiny, dense nucleus at the center. This nucleus was incredibly small compared to the overall size of the atom, yet it contained nearly all the atom's mass.
Rutherford's experiment revolutionized our understanding of the atom. It marked the beginning of a new era in atomic theory, challenging existing models and paving the way for future discoveries. It revealed that the atom was mostly empty space, with electrons orbiting a small positively charged nucleus. This new model provided a clearer picture of atomic structure and helped explain many previously puzzling phenomena. This model, with its resemblance to a miniature solar system, became the iconic image of the atom. The electrons orbited the nucleus much like planets orbit the sun, a concept that was both intuitive and revolutionary.
However, it also presented a major problem. According to classical physics, electrons orbiting the nucleus should continuously emit radiation, lose energy, and spiral into the nucleus, making atoms unstable. This paradox highlighted the limitations of classical physics and set the stage for the development of quantum mechanics, which would eventually resolve these issues and provide a deeper understanding of atomic behavior.
The stage was now set for another bold leap in our understanding of the quantum world. The early 20th century was a period of rapid advancements and groundbreaking discoveries in physics. Scientists were beginning to unravel the mysteries of the quantum realm, challenging long-held beliefs and opening up new avenues of thought.
In 1924, I, Louis de Broglie, a French physicist, put forward a radical hypothesis. My idea was inspired by the dual nature of light, which had been demonstrated to exhibit both wave-like and particle-like properties. This duality, first proposed by Einstein in his explanation of the photoelectric effect, led me to ponder whether matter could also possess such dual characteristics. If light, which we typically think of as a wave, could also behave like a particle, as Einstein had shown, could matter, which we perceive as particles, also exhibit wave-like properties? This question was at the heart of my hypothesis. I proposed that every particle of matter, no matter how small or large, has an associated wavelength, which is inversely proportional to its momentum.
De Broglie proposed that all matter, from electrons to baseballs, had an associated wavelength inversely proportional to its momentum. This was a revolutionary idea that suggested a fundamental connection between the wave and particle nature of all entities in the universe. The implications of this hypothesis were profound, as it meant that the behavior of matter could be described using wave equations. This meant that objects with smaller masses and higher speeds would have more noticeable wave-like behavior. For instance, electrons, which are incredibly small and can move at high velocities, would exhibit significant wave properties. This was a stark contrast to larger objects like baseballs, whose wave-like behavior would be imperceptibly small due to their larger mass and slower speeds.
This idea, known as wave-particle duality, was met with skepticism. Many scientists found it difficult to accept that matter could exhibit wave-like properties, especially when it came to everyday objects. The concept challenged the classical understanding of physics and required a shift in perspective that not everyone was ready to make. It was hard to imagine everyday objects like baseballs behaving like waves. The notion seemed absurd to many, as our daily experiences did not align with this idea. However, the beauty of science lies in its ability to challenge and expand our understanding of the world. even if it means questioning the very nature of reality. However, my hypothesis found experimental support a few years later. The scientific community began to take my ideas more seriously as experimental evidence started to emerge. This evidence was crucial in validating the concept of wave-particle duality and demonstrating its applicability to the behavior of matter.
In 1927, Clinton Davison and Lester Germer in the United States and independently George Paget Thompson in Scotland observed the diffraction of electrons by crystals. Their experiments provided the much-needed empirical evidence to support de Broglie's hypothesis. The diffraction patterns they observed were similar to those produced by waves, confirming that electrons could indeed exhibit wave-like behavior. Diffraction, the bending of waves around obstacles, is a characteristic wave phenomenon and had been previously observed with light and X-rays. The fact that electrons, which are particles, could produce similar diffraction patterns was a groundbreaking discovery. It provided a tangible demonstration of the wave-particle duality of matter.
The Davison-Germer experiment confirmed my hypothesis, showing that electrons, and by extension, all matter, could indeed exhibit wave-like behavior. This was a monumental moment in the history of physics, as it bridged the gap between the classical and quantum worlds, providing a deeper understanding of the fundamental nature of reality.
This groundbreaking discovery blurred the lines further between the classical and quantum worlds. It opened up new possibilities for research and experimentation, paving the way for future advancements in quantum mechanics. The concept of wave-particle duality remains a cornerstone of modern physics, influencing our understanding of the universe at its most fundamental level.
If you enjoy this channel, don't forget to hit that follow button. Your support drives my creativity, and together, we explore the wonders of science. Let's make discoveries together.